is really going to be chapter 8 material. This is going to be propagation from antennas, electromagnetic radiation from antennas. The whole chapter is termed antennas. And I'm going to mention a few things before I start this. There's almost an assumption, the way this book is presented, that we know what an antenna is. An antenna simply takes electromagnetic currents and creates really radiated electromagnetic fields, but packets of photons. So it's an energy conversion transducer in that sense. Y'all follow me? An antenna is something that takes currents, really. Has to be an accelerating current for a radiated field to occur, or excuse me, accelerating charge for radiation to occur. And it creates a launched electromagnetic wave. It's important that I'm clear about this. You all remember me giving you a little talk about things that are propagating and fields that are resonant or the energy can be gotten back, right? All right, with a capacitor and an inductor, there is an electric field around a capacitor, even if there's no time-varying state. You all agree with that? The energy in that field can be brought back to the capacitor and discharged through a resistor. If you just take a charged capacitor, put a resistor across it, all that energy will dissipate in the resistor. You all with me on this? Now with an inductor, again, that current will create an H field. If you just have a DC current, the H field's around the inductor. It has an energy density of 1/2 mu H squared. And if you want to get the energy back, you can put a resistor across that, and all that energy will come back. The difference between those two situations and what we're terming it as an antenna is that the electromagnetic field created by that antenna, at least the portion we're interested in, is launched. It's photons that are never going to be able to come back. All right, y'all with me on that? So that's what we're after. Now, most of you, when I say the word antenna, think of something in your mind. Parabolic dishes that are used to receive GPS, or not GPS, but the actual geosynchronous satellite signals for your TVs. Y'all know what I'm talking about? You think of the old car antenna, which was an aerial, sometimes it was called. It was just a straight piece of wire that you could extend, right? There's antennas that are made, a lot of antennas are parabolic, but there's also antennas just arrays of long pieces of metal. The most common antenna that you're probably familiar with, I don't know, did you have an antenna lab at all yet? In physics, you did have one, though? Where did you have it?
It was RF, that was what it was.
How many had RF lab? All right, then you know exactly what antenna is. Wentworth's lab? And usually they start with a straight piece of wire that's considered very thin when we do antenna analysis, and they're going to define what the current is on that antenna. Now there's a lot to this that is not said in his book, but I've got to start from there. So based on that, in his book, on the first page of 427, he shows what a lot of antennas look like. And they're just like what I said. There's nothing there. Now the way Whitworth's book is laid out, he talks about the properties of an antenna without you solving Maxwell's equations, which is required to get those properties. So I start by solving Maxwell's equations. I get them to a point, just like we do with wave propagation. I make assumptions, and then lo and behold, we get something we can use to develop the field equations from antennas. Okay, with that, everyone? So I'll tell you, if you're following along where I start, I don't do his first part that way. We come back and do that. What I do is, hasn't rearranged this. Okay. In his book, and this is some crazy stuff here. It starts on page 438, section H2, and he starts with the vector electromagnetic potential. Let me start there, and I really want to be fair with you about this. This is extremely ambiguous, and I'm going to tell you why. First, this is a fictitious vector quantity. Only the gradient and divergence of this vector quantity are measurable. But the reason we use it is because it helps solve the mathematics easily. That's the reason. It's called A. So this, he introduces the term A. The definition is the magnetic vector potential. And it's a fictitious quantity in the sense you can't measure it. But it's mathematically rigorous and it's related to the H field and the E field. The first thing I'm going to do is show you the relationships. The curl of A, curl of the magnetic vector potential is equal to the B field. And the B field is equal to mu times the H field. Are you with me on this? I'm just showing you. Remember B equals mu H class? I'm going to do this in a way that I would want it shown to me. So it's logical. That means the H field is actually equal to the curl of A over mu. This doesn't tell you much at all. I'm just showing the relationships. The next is its relationship to E. And E is equal to, here it's the curl, it's going to be, the way he writes it in his book, I gotta make sure it's time frequency. I don't actually know if he puts it in there. Well, before E was minus the gradient of the voltage, right? Remember that? And it's also minus dA dt. There's two forms of this. Now, I've got to say something about this. E, this is true always, for propagation or non-propagation, will always be minus the gradient of voltage. That voltage comes from the charge only, not the current. Y'all follow me on that? Remember, charge was related to voltage. This will come from the current. You're going to see more about this. Now, here's the reason I'm showing you this first. You kind of have a fair handle on what voltage is. And a bit of an idea about H, a bit of an idea about propagating E. But the thing about this is, if the curl and the divergence of a vector are specified, it's unique. These are the relationships to the field quantities. And here's how we get the divergence. When we start out with the curl of H equal to J plus the partial of D with respect to T, that's the general form of the Maxwell equation we call Ampere's law. Now I'm going to put in the assumption, if we go to the frequency domain, that the time derivative brings about a J omega in front of the time derivative, and replace E with sigma E, or J with sigma E, and D with epsilon E. But I'm going to do one other thing. J, remember, represents all forms of real charge moving through the lattice that aren't bound. Y'all remember that? There can be an impressed J, so that's the reason I'm saying that. This would be J impressed, and it would be like from a chemical reaction inside a battery. Y'all follow me? It's something that's forced, not due to the electric field in any way. Y'all follow me on this one, class? If you literally grab the whole of an electron and drag it through the lattice, that's the kind of J I'm talking about. It's forced to occur, but it is not a result of the electric field's impressed value. Right? Now when I do this, I can say, now I'm going to go ahead and go to the frequency domain. First I take curl H and I replace it with that. And then I get curl of A over mu. I'm just taking H and replacing it by curl of H. And then I get J. Well, J is equal to sigma E. And E is this, minus the gradient of V. As a matter of fact, let me do this in the frequency domain. So E itself would be equal to minus the gradient of potential minus J omega A. That way, it'll simplify things. If I bring J omega into it right now, and it's going to be minus J omega A, then I get plus J omega epsilon times E, which is minus the gradient of V minus J omega A. And finally, I get plus J impressed. Now I've done that, and a lot of you, I'm just doing this so you appreciate where we're going. You don't have to know how to do this. I just want you to appreciate it. If I don't do this, you won't see why some of this stuff falls out. Now, the curl of A, what I'm going to do next is straightforward. I'm going to go ahead, I'm going to try and simplify this as quickly as possible. See this 1 over mu term here? It's irritating. I multiply everything by mu. That's the first thing. Okay. Just multiply, it's a constant. Yes?
You need me.
Oh, yeah. You're right. You're right. Thank you. Everybody with me on that? Now the next thing is I'm going to take this and I'm going to use that vector identity. You remember that curl of A, or curl vector identity? I'm going to do it right here. Now I get I get the gradient of the divergence of A minus del squared of A. If I had a nickel for every time I did this, I'd be a rich man. I've had to do this so many times in papers and proofs and other things in front of people. It's something you won't believe you have to do, but you do. Equal. Now I break this stuff up, and you can see it's going to be minus mu sigma gradient V minus mu sigma, it's actually minus J omega mu sigma times A minus J omega epsilon mu times gradient of V minus, and then here it gets kind of interesting because it's going to be minus J times J is J squared, so it's actually plus all right. I just went ahead and broke the whole thing down. Are you with me? All right. Here's what happens next. I'm going to separate all the terms except for this divergence of A term. This term, this term, this term, and this term, all in an equation. Y'all, just hang on. You'll see this will work. So I'm going to go ahead and say, let me do this in a way that will make sense. Actually, I'll do this part first. I'm going to take the gradient of the divergence of A here. That's on that side. That's going to be equal to all the stuff that has gradient V in it. Is equal to minus mu sigma gradient of V minus J omega mu epsilon gradient V. And this is going to be true. And then I'm going to take this minus L squared of A on that side is equal to minus J omega mu sigma A plus omega squared mu epsilon A and plus mu Ji. Now, what I've done is, if this is true and this is true, that is true. Y'all follow me? I took this equals portions of this equals portions of this, and if you take them both and add them up, you get that. Are you with me, class? Now, why did I do that? Here's why. I want you to look. Remember I said earlier that if the grade or the curl and divergence of any function are specified, they are unique. You all remember that? You're going to have to take my word on it. It's true. I can prove that, but not in this class. If you want to see the proofs, come to my office after too. If the gradient and divergence of any mathematically exact function are known, then that function is unique. In other words, they can't have two values at the same time. So if I look here, you see that gradient operator appears everywhere? Are you with me? What that means is I can take it out of everything and put it outside. Now that's true if sigma and epsilon and mu do not vary spatially, and that's an assumption. Y'all hear me on that? If they did, you can't do this. And there's a paper I had in Nature about this. It was one of my first publications. Actually, I think it was the first and only publication in Nature. But I remember this very, very well. You can't do that, but this is a common assumption. Now, look, if this thing, remember, this can be, now what I have is a gradient of a function, right? Well, what they do is say, if that right there is true, the gradient of that has to be true, right? And if you look at this carefully, this is what's called a gauge condition, because it has the divergence of a vector equal to something else on the other side. You all with me? And this is called the Lorentz gauge condition. Actually, they don't even put the gradient here. They say when this is true, or the way they usually write it is this. And they'll put the whole thing equal to 0. You don't have to know this, but at least you have to have an appreciation where it comes from. If that's true, and then they'll factor V separately, and they'll have mu sigma plus j omega mu epsilon, and then they'll have V on the outside equals 0. If that's true, and you can take V to the other side if you want, then you have what's called the Lorentz gauge condition. And now you define the divergence. And I can put the V on the other side if it makes you happy, but you don't have to. Do you all follow me in this class? Now it's unique. And now if you solve this for A, and I'm going to clean this up a bit, and I'll show you the actual form. If I take this and I solve it for A, the way it usually appears is del squared of A, all right? And then it'll be minus j omega mu sigma A plus omega squared mu epsilon A equals minus mu ji. Then they solve that for A, and after they get A, then they get H using this equation. And furthermore, the way they actually get E in the book is if I have H, I know that the curl of H is equal to sigma plus j omega epsilon times E, and they'll get E simply by taking the curl of the solved value of H right here, and they'll say E will be equal to the curl of H here over sigma plus j omega epsilon, and that's how they get, Stu gets E in the book. So if you have A, you have H by a simple curl, mathematical curl. If you have H, you have E by another curl. You with me? So that's the idea. Now, the obvious thing is, well, I have no clue about it. What are the boundary conditions? How would you go about solving? I'm going to make it easy for you, because this is a lot of this stuff teeters on graduate work, some of it doctoral work. It's a little beyond mathematically what we're capable of here. See this right here? And I said that's the forced known current, right? Well, we know, or we couldn't solve the problem, the current's on an antenna approximately. So if we know that, we can solve this differential equation. Usually it's solved in spherical coordinates. I'm just telling you. And what they do for this, how many have heard of delta functions? Or impulse functions, direct delta functions, right? In your signals and systems course, an impulse function was something you were introduced to the concept of, right? That was in time. It was delta t or delta t minus something, right? There are spatial delta functions. What they do is define a delta function on the antenna surface that turns on, and its value is 1, only when it's in the antenna surface. Remember the discrete delta function would have a value of 1 or 0? That delta function will be spatial. It will be like if it was an x, y, z. Delta x, delta y, delta z if it was at the origin, or they would have the actual displacements if necessary. It turns on there, and this has a value that's non-zero. And the J would be the current density associated with the antenna we're talking about. Then they go about and solve this differential equation, that being a delta function, and they can solve it usually, I think, with Laplace transforms, but they're spatial Laplace transforms. you're used to doing Laplace, this is why it's so far beyond what we normally do in this course, but I'm just giving you something to appreciate. Do you all remember when you had Laplace transforms, they were time right to s? Do you all remember that? The way we do them, and it doesn't matter, we do space, we'll do like x to s, y to say t, or I mean not t, z, and then whatever, z to some other variable, usually Greek letters. Do you follow me? Laplace transforms work no matter how you're doing it, time or space to some other fictitious domain. But when you do it, these become they become algebraic equations that are easy to solve. That's what I'm getting at. Now, I'm not going to do that because that's well over what we're going to cover, what the basis for this. But I do want to make sure you understand that's how it works, all right? We get A. Now, Wentworth, what he does in his book is kind of nice. He just says, aha, I won't show you how this works, but I'll give you something that has to be true if what I just showed you on this board is true. He says that A, now this fictitious vector quantity, is actually definable, and it is a solution of that equation I just put down. I'm not going to solve it. As mu over 4 pi times the integral, you're not going to like this, of j here, and I don't like his notation. I'm just going to tell you it. He shows you this on 441 on the equation 8.38, but it is a nightmare to understand. So what I do here, I'm not going to put j in, I'm going to make it a little more real. I'm going to say if we have an antenna here, then we know this antenna is in the z direction, and we know at some point here, some actual differential, or I'll call it, I'll call it I right here of z. And I know what I is a function of the height z. Then this will be the integral of I of z times e to the minus j beta. I'll put that up there in a second. This is going to be the distance. If this is I of z and I wanted a here, this right here is going to be my r prime over, and this is going to be over r prime, and then it's going to be dz from 0 to the length of the antenna. Let me make a comment about this because this makes no sense to you yet. All right. Usually speaking, the measurements in spherical coordinates are measured from the origin, and that's r. You all follow me? Now, because this point is assumed far away, the path difference here is going to be related to the cosine of this angle. I'm not going to get into it. I'm just trying to tell you where it comes from. You with me on this class? And really, what should be said, if we're doing this r here is really that r, so it can come outside. And this r here, just like when we had the array or the point, no, we didn't do point sources here. That r prime is really going to be equal to the actual r there minus, and then whatever the height is here, this distance will be z cosine of the angle theta here. And that would go there. Matter of fact, I can put it in.
So theta is the angle between the z-axis and our prime?
Yeah, and what I should do is say, I'm not going to get into this. When I look at, this theta is true theta that you're used to. It's measured from here to the r vector, but it's assumed that this is the same as this. All right, so we're a long way from the antenna, basically. And then when you get this, it breaks down to mu times e to the minus j beta r over 4 pi r right here, and then you're left with this integral of I of z times e to the minus j beta z cosine theta dz from 0 to L. That's the way in Wentworth's book he's going to have it. I don't want you to worry about that. That's what he's showing you. Actually, this is 8.42 in his book, but he goes from minus L over 2 to L over 2. Frankly, you can go from 0 to L just as easy. But here's the thing we do. Now this is where you start paying attention. The first assumption in Wentworth's book. All right, when we talk about this antenna here, I'm going to redraw it just to make sure I'm clear. They're assuming the length of this antenna, L, and this is where I of z is. L is much less than a wavelength, or less than lambda over 10. So he's going to assume this is a short dipole. Write this down. This is important. So he's assuming that what we're talking about now is a little chunk of current that's very short. You with me on that? Everybody? And if this little chunk of current is much less than a wavelength, then the phase or the value of I at this point is about the same as the value of I at this point. Y'all with me? In other words, it's a piece of current where nothing's changing. That is the inherent assumption. And he says if that's true, then this equation, forget that integration, everything becomes a scalar, and therefore I, right, or the A vector potential is simply mu times I, whatever I is, whatever that value is, I naught, times e to the minus j beta r, right there, over 4 pi r, and it will be in the AZ direction. The vector sense is important. And I'm trying to make sure I address every concern with that. Also, it has to be times L. Now, this is the one, write it down. But I did it without doing, I'm not using his notation. The R vector there is from the origin. It's measured from the origin. You with me? Here's there's no real trick here. L is the length of the antenna in meters. I is the value of the current. And it's assumed upward. It's in the AZ direction. Now, when you go ahead from that point, and look, I know this is a little unsatisfying, but I'm trying to give you a glimpse of how it's actually arrived at. When you do the differential equation solutions, you get that stuff. And it's very hard to appreciate where you're sitting. I know that, so I'm doing my best to make you at least understand where it comes from. You should have that in the back of your mind. So if that's A from the short wire, then if I take that, and remember, I want the curl of A to get H, right? Now I want to tell you there's an assumption. The assumption is we're far away from the antenna, but I should say here, and it's not stated explicitly, for this to be true, R has to be much greater than L. You've got to be a long ways from it, or else it won't work. All right, when you're right up butt against it, this doesn't work. Then you get those fields that are going to be stuff that's got energy you can get back, evanescent fields. But when they do the curl of H, what he does is he'll take this and he'll turn it in to spherical coordinates. Now just listen to me here. All this stuff is in spherical coordinates here. I mean, the R's are, but this isn't. So what he'll do is say, this is really equal to the curl in spherical coordinates of that, which is mu0 I naught over 4 pi r, that's spherical coordinate r, times L times e to the minus j beta r. But then you see this AZ? Now he takes AZ and he turns it into its spherical coordinate equivalent. And remember, with AZ it goes up like this, right? So it has a value, maybe I should extend it like this. It has a value of projection here, which would be in the AR direction, and that's weighed by the cosine of theta. And it also has a projection, and this would be the phi direction, it's a 90-degree angle. And this one, I should say, yeah, that's right. This is going to be minus a theta, pardon me, times the sine of theta. And that would be this and this would equal AZ. So what you'll have, if you look in the book, is you'll have AR cosine of theta minus A theta times the sine of theta. And the only thing he's doing is converting AZ to spherical coordinates. And that's in equation 8.44 if you want to make a note of it. Y'all hear me on this, class? It may be boring. It may be like, why are we doing this? There's a reason. You'll see a lot of this in a second. Now, once we have this, y'all agree we can execute a curl in spherical coordinates, right? In the back of your book, right? We can do that. I'm not going to do it right now. But when you do the curl in spherical coordinates here, then you get the H field that's due to propagation. Then you do another curl to get the E field. I'm not going to do it right now. I just want to give you a glimpse of this. What we're going to find is we'll have a solution for both the E field and the H field from a little chunk of current. Just like we had A here, we'll now have E and H for that little chunk of current. So when we want the total E field due to an antenna with some link, then we integrate the differential amount of, we basically sum, but it's really an integrate the actual differential electric field that comes from a little chunk over the entire wire to get the total electric field or the total H field. That's the goal of this, right? No matter how I present this stuff, it will not, I never feel like do justice to it because I want to do the full proof, but it literally takes about 2 hours to go through from scratch and show you how to work this stuff with to solve the differential equations. It's a long proof. So now, the thing you're all going to wait for. Fill up this first row, move the guests over there. Leave this row empty, fill up this row.